on behalf of the Governing Council of the Hellenic Astronomical Society, I would like to introduce today's speaker. We are delighted to have with us today Dr. Leonidas Moustakas of the Jet Propulsion Laboratory in Pasadena, California. Dr. Moustakas got his bachelor's degree from the University of Arizona in 1991 and his PhD from UC Berkeley in 1998. Then he moved across the Atlantic to the University of Oxford in the UK as a postdoctoral fellow there. And 3 years later, in 2002, moved back to the States as a postdoc at the Space Telescope Science Institute, where he worked on Spitzer. And then in 2005, he joined the NASA's Jet Propulsion Laboratory as a staff scientist. And this is where I met him also in 2008. Since then, he has moved up the ranks, and now he is a manager of the Astrophysics and Space Science section. Dr. Moustakas is an expert on on the galaxy formation and cosmology in general. He's interested in the nature of dark matter, and he will talk to us today particularly about the use of strong lensing to infer the cosmological big mysteries of dark matter and dark energy. What I can say as a personal note is that Dr. Moustakas is not just a brilliant scientist, but he's also a wonderful person. So without further ado, thank you, Leonidas, for giving this talk today. You have the floor.
Thank you, Costa, and thank you for the gracious invitation and introduction. I am delighted to be here and to share this virtual moment with everybody from Greece and from around the planet. Let me begin with a visual, a quick overview. So I grew up in Megara, outside of Athens, and this picture on the left is a little snapshot I took a couple of years ago from Paki, which is the marina of my hometown. And on the right, you'll see a picture of the area where I live and work now in Pasadena, California. And you might see that the mountains look really similar. There's a reason why I've ended up here. And the only thing that we're really missing is the Mediterranean Sea, which I do miss dearly. But the mountains, and because I am the cook here, the food is also very much like Greece. But I hope you can all come and visit sometime if you haven't been here before already. So I'd like to start by just framing some fundamental questions in astrophysics, which is how I love to think about science. This is a snapshot of the Hubble Ultra Deep Field. It is one of the deepest images in many different wavelengths of a tiny, tiny patch of the sky. And it is completely full of an enormous diversity of luminous objects spanning many decades of mass scale and luminosity scale, up to and including some foreground stars that are from our own galaxy. But as we've learned over centuries of study, and certainly from over the past 50 years, this is literally just the tip of the iceberg. And if anything, it's motivated some of the truly fundamental questions in astrophysics that we are working on today. So there are small numbers of questions that one can pose that encompass human curiosity on these cosmic scales. The ones that I keep gravitating to, I would summarize into these four. Is there life beyond Earth in the universe? A spectacular question that I really feel we're going to learn a lot more about in the next 5 or 10 years. What makes life possible anywhere, including on planet Earth. And so understanding the nature of water and chemistry in the universe is an area that will give us deep insights into the nature of humanity and the cosmos. And then going into much broader scopes, the nature of dark energy that drives cosmic acceleration is something that has an easy sounding term, dark energy, but that encodes mysteries about field theory and how the universe actually operates that we haven't yet to decipher. And then finally, what is the nature of dark matter? The material that we know provides a gravitational imprint in the universe, but whose nature we don't yet understand. And we know the numbers behind these questions to an incredible level of precision from a cosmic microwave background and many other studies. We know how much dark energy there is in the universe and how much dark matter there is in the universe, and also how much material there is that can make up planets and stars and the gas between everything. But the satisfying answers to these questions are as yet to be fully deciphered. So I am going to bring a tool to explore directions towards answering these questions. And I really love working with tools in astrophysics. And so strong gravitational lensing is going to be the theme of my discussion with you today. So gravitational lensing, actually, let me pause a second. So Costa and my hosts, I am very comfortable being interrupted. If you like to curate questions from the chat discussion or anything, I'm very happy to weave in discussion questions or general questions as I'm speaking. So do not hesitate to interrupt me. I'll be fine with my flow. So lensing is a phenomenon that we witness every day, whether you're down at the sea, in the Mediterranean, or in a pool. You will see these ripples, which are basically caustics, areas of what could be infinite magnification that derive from the refraction and imperfections in the surface in the transition between materials, between air and water, between glass and air, or between other materials. And I'm really fond of this picture on the right, which I neglected to give credit to. This is a picture that Phil Marshall composed some time ago. If you take the base of a wine glass and you tilt it just so in front of an incandescent light or a candle or some clear and not too bright source like that, as you change the angle because of the refraction and the varying levels of thickness in the glass, you can create multiple images, you can create double images, you can create a full ring of light. And this is basically lensing in an everyday experience, and I encourage you to observe this next time you are either holding this kind of a glass or next time you're at a pool or a tub or the sea, and enjoy these patterns. Because the same kind of patterns can be observed in nature as well. Now, this is a classic Euclidean style geometric diagram of gravitational lensing, of lensing actually in general. And what you can end up seeing is, if refraction is possible, if you can get a sufficient amount of material along a line of sight, which is the yellow plane here that I've labeled as a lens plane, a more distant object, which I'm calling a source, that's over there on the far left in the source plane, could end up being lensed in the same fashion as what we did with the candle and the wine glass to produce multiple images of the same object. So this is a basic geometry problem. You can actually do this with a vector description of the geometry of the situation in a, I don't want to say a trivial way, but in a very straightforward way. So if you were to work this out on the back of a napkin, you'd be able to do this with just a little bit of a geometric manipulation. And this is maybe a little more graphically pleasing representation of the same diagram. On the far left, it's a model galaxy. The lens plane is a massive galaxy with all sorts of features that might have stars and giant molecular clouds and dark matter and things that we are going to be discussing more. And this object can be distorted into these multiple images that can compose of a full ring of the galaxy. And if there's a bright point source in the center, you can see that as well into multiple images. An equation, a recasting of that geometric equation that I'm extremely fond of is one that connects to the amount of time that it takes light to arrive to us. So on the left, the tau is the light travel time of a photon as a function of position on the sky. And this leading term that I have highlighted is the term that describes the relative distances between us and the lens and the source, and the distance between the lens and the source. The quantity in the right in the brackets, it describes the gravitational potential and the geometric alignment between these different components. Now, I love this equation because it allows you to develop an intuition for what is actually going on when you can form multiple images. So the contour diagram you see on the left here, on the bottom left, is showing you literally the contours of the arrival time of light as a function of position across the sky when you are in a lensing type of an environment. And this equation describes everything that you need to know or would like to know about a lens. And we're going to get into this in some more detail. What I want to highlight at the moment is that when you get these lensing environments, this quantity that I have highlighted, that I've framed, is entirely composed of geometric distances, of angular diameter distances between things, and the redshift, which is the cosmic expansion metric, to the actual object doing the lensing. So in this kind of a geometry, you can already see that you might be able to do cosmology. You might be able to measure distances. So I wanted to highlight, before we get into this in more detail, that there are many gravitational lenses that we have discovered. The first one discovered in 1979. And right now we know thousands, we've discovered thousands of such systems. And if you start looking at images like these, like what I'm sharing here from a variety of publications, you can start developing a visual intuition for what might make a gravitational lens. So if you happen to be looking at some astronomical images or on the web or in the literature, you can start visually decoding what could be a gravitational lens and go from there. So as I mentioned, there are thousands of strong gravitational lenses that we've discovered to date, which is spectacular. Back when this phenomenon was first predicted by Albert Einstein, as with so many other things, he basically did a back of the envelope calculation to describe basically the geometric equation that I outlined earlier, and was confident that this will never ever be observed. It did take a few decades, about 40 years, but after the first object was discovered, this two-image lensed quasar called Q0957, many others have been discovered over the years, and the pace of discovery has been accelerating. I'm very excited about Gaia-based lenses based on astrometric positions of quasar-like color objects. I'm excited about the dark energy surveys discoveries, many other surveys. And the thing to get excited about is that over the next 10 years, by the year 2030, we expect to have discovered hundreds of thousands of these objects. The fundamental question is always, who cares and what can we do with these objects? So one of the first ingredients that you need is the ability to simulate objects like these. And there are many different Python and other code packages that are available. If you're interested in playing around with Python notebooks, Jupyter notebooks, things like that that you can use for yourselves or for your students, I recommend taking a look. Lenstronomy by Simon Burr is just one of many that are really crafted to be easy to use and to learn from and to develop an intuition about what is possible. It's fun to see how these kinds of phenomena can unfold in front of you. So let's start by doing some of that cosmography. How can we measure things about the universe with gravitational lenses? So if one wants to use the arrival time equation, the light travel time of photons, and this leading term that we spoke about just for a couple moments, well, you need to see what the difference might be in light travel time between different images. That means that something has to actually vary with time. And there are quite a few things that, as the expression goes, go bang in the night. There are quite a few things that are visually transient in their brightnesses in the universe. And there are many more than the list that I've made here of quasars, supernovae, gamma ray bursts, fast radio bursts, gravitational waves, and so on. And if they happen to happen in an environment that can be multiply imaged, gravitationally lensed, and we can actually observe it, then we can use it. So the difference in light travel time between these different images is what we are going to be honing in on for a few minutes. So let's start with one phenomenon that you may have heard of, you might be very familiar with, quasars, or active galactic nuclei. So these are supermassive black holes, and by supermassive, we mean between 1 million and 1 billion times the mass of the sun. These are at cosmically far distances from us, generally speaking, and they tend to be in the centers of very massive galaxies. The very center of quasars, where the accretion to supermassive black holes is taking place, are very small in scale. They're just light days in physical scale, but they have a lot of structure to them. And so between the accretion disk, which has variability timescales of minutes in the accretion disk to days further out in the accretion disk, to the broadline region, which corresponds to larger distributions of material around the black hole, to the narrow line region, so-called, which is sort of the scale of the host galaxy itself. There's a lot that's going on, and the brightness can vary in many of these different physical and light travel time scales. So in fact, this diagram on the left is a power spectrum, and we don't need to get into that in detail. The point is that on different time difference time scales, there are variations happening all the time. There are larger variations on small time scales and slower amplitude variations going on longer time scales. So if you observe a quasar right now and a week from now, it will have varied. And by this kind of power spectrum description, we can encode a probabilistic description of how much the quasar may have varied. So we know this, we've observed this. This figure on the left is actually derived from a combination of hundreds of different objects, variations, quasars variations. And here on the right, we see a lensed quasar, one of my personal favorites, HEO 435. One gets used to the phone numbers of these objects. And this is from no less than 13 years of measurements from the CosmoGrail project, which is a European-based project doing spectacular work for literally decades in monitoring the variations of lensed quasars. And what you see here on the bottom right is the light curve variations over 13 years of each of the 4 images in this single quasar. And we're not going to get into it in gross detail right now, but you might already be seeing that there is some family resemblance, the variations between the images. So on the one hand, the quasar is varying a lot. On the other hand, you can see that there's a slight offset between the variations between the different images. And that is exactly what we can use. I do need to add one more layer of complexity. There's going to be layers and layers to this presentation. But you may have come across the fact that the stars in the lensing galaxy can lens the quasar as well. And that is over and above what the entire galaxy is doing. So in this lens image on the left, which is a model of another one of my favorites, RxJ 1131, you see 4 images. They're a little blurred because this is representing a ground-based kind of an image. But you can see the lensing galaxy and the 4 images. And if one could, through imagination or through modeling, zoom into what each image actually looks like at the micro arcsecond, so 10 to the minus 6 arcsecond kind of an angular scale, you will begin to see that the gravitational impact of individual stars is actually of comparable scale to the accretion disk of the actual quasar. And the caustics that I referred to earlier in showing you the image of a pool happens from all of the individual stars. And this third panel here on the right is showing what a pool-like caustic network looks like by the ensemble, the combination of the stars in the lensing galaxy. Now, the reason I'm telling you this is because it's signal and it's noise, because individual stars can actually my audio dropped and reconnected. So this should be working. I apologize for that interruption. So you can get magnification and other variations from the stars themselves. So we are ready to piece things together. Here at the top right, there is a simulated, an animated version of variations that I hope are coming through in the Zoom connection. But this is just reflecting the intrinsic variation of the quasar that we're seeing in a delayed fashion between each one of the images with an extra differential in magnification for microlensing added on top of that. So you have to put all these ingredients together in order to begin to decode cosmology and other intrinsic events that a gravitational lensed quasar is telling us. Now, there have been several projects working on this in order to calculate that leading term that encodes Hubble's constant or local expansion and other cosmological parameters. And this is pretty exciting because Hubble's constant has been measured to an insane level of precision, to a percent or so by the constant Makareyev background. And here from this popular article graphic on the right, I'm showing what the European Space Agency's Planck mission has determined for Hubble's constant. And it's about a value of 67 kilometers per second per megaparsec. But for many years, the Hubble's constant measurement from Cepheids using the local distance ladder from the SHOES project and from the Carnegie projects have suggested that Hubble's constant as locally measured might actually be a almost equally precisely measured different value. And so there's some speculation as to whether there's actually tension or something interesting in cosmology that might be room for new exciting discoveries, or whether we are just not controlling systematic uncertainties or other effects sufficiently well. So gravitational lensing and lens quasars have been coming into that fray. And here on highlighted with a red arrow, I'm showing one of the collaborations led by Sherry Suyu in Germany, who's been doing fantastic work with her collaborators in trying to really dial in the measurements and the uncertainty determinations in these kinds of gravitational lens systems. So in fact, here on the on the left, there's another summary paper by the so-called Holy Cow collaboration by Sherry Suyu's group. And this is from the Wang et al. Paper from 2019, showing for a variety of different approaches to the measurements, what the Hubble constant measurements are from gravitational lens quasars compared to the Planck measurements. And there's clearly room for possible concern. But another group, the TD Cosmo group with Simon Burr and Tommaso Treu and collaborators, have been taking their own systematic measurement approach to the Hubble's constant measurement. And this is really fun because this summary plot by Simon Burr from just a few months ago puts together their analysis of the same or similar data as the plot on the left, again from gravitational lens quasars, and has done the analysis a variety of different ways. And what I want you to take home from this measurement is that there is still room to really understand what's going on. You see at the bottom left of the diagram, there are measurements that might be more towards the Planck values. And so I'm excited about this field. It's one that I have just begun to be working on for this particular combination of measurements, because I've been working on all the ingredients to this and seeing the synthesis showing how much more work needs to be done. But this is also a lead into another topic that I am working on, which is using a different transient. In my abstract and at the beginning, I did promise sort of a sweeping overview of a variety of really exciting techniques that are tied together by the tool and method of gravitational lensing. So I hope you'll bear with me, and I do hope you'll keep note of questions or points that you'd like me to expand on. So let's go ahead and go forward. I did say that in strong gravitational lenses, if you want to do cosmography, you just need a varying brightness object. We talked about quasars. Now let's talk about supernovae. So supernovae are exploding stars. And if you have a galaxy, stars will explode. And if you have a lensed galaxy, stars will explode. And you might see them in multiple images in gravitational lens configurations. So there are many kinds of supernovae, but the two large classes that we have found the most useful over time are the type 1 supernovae, which are expected to come from white dwarfs, merging white dwarfs at the very, very end state of stellar evolution. And so they tend to be delayed from when stars have actually begun to form or the star formation history. And the type 2 supernovae, which are extremely massive stars at the end of their individual evolution. And so type 2 supernovae tend to be more directly correlated with what level of star formation is going on in the galaxy right now. So you can see that there's a connection between old stellar populations for type 1 supernovae and actively star forming younger stellar populations for type 2 supernovae. So I do want to mention here on the far right, you can see what typical light curves might look like. So type 1 supernovae have a very characteristic light curve as they brighten and then dim following a particular combination of radioactive decay of elements. And the type 2 supernovae, which has a different combination of elements that are producing light, as well as the expanding photosphere as it cools, is diminishing in light over time. And there's a lot going on, but it is a varying light source. And if you have a supernova go off in a lensing environment, you can expect to see the variations to pop up in different positions around your lens galaxy over time. So the reason I'm mentioning this is because they have been found and there are prospects for many more. Let me dig into that a little bit more. So this was a very exciting discovery. This is a real Hubble Space Telescope image from a very massive galaxy cluster. I've not spoken about galaxy clusters, but they can be 1 trillion times the mass of the sun, 10 to the 12 times the mass of the sun. And they too serve as incredibly powerful gravitational lenses, and they can lens background galaxies and supernovae inside of background galaxies as well. So lens supernovae have been discovered in such systems, and there are several systems where we've predicted when future lens supernovae images will occur 10 or 15 years in the future. So this was an exciting discovery a handful of years ago, and it shows that this is a real thing. So on the basis of, well, the need to understand more, how can you actually tailor observations to do a really good job on discovering and measuring properties in lens supernovae, especially to anticipate what will be possible for the future. With several collaborators, I'm part of a program called LensWatch, where we have been awarded Hubble Space Telescope time to activate what's called targets of opportunity observations of potential lens supernovae that we are looking for in real time using a variety of ground-based monitoring projects. There are several. There's Pan-STARRS and other. The most productive on a nightly basis is the Zwicky Transient Facility, which is observing the entire Northern Hemisphere on a very regular cadence. And between that and other projects, there's the opportunity to monitor on an hourly basis what is going on in the sky and to seek out potential gravitational lens supernovae that we would then trigger to make Hubble Space Telescope observations of. The targets we are observing are the whole set of known strong lens galaxy lens systems. You saw this diagram earlier. This is just a tiny fraction of the now thousands of galaxy lenses, where the background object is a galaxy forming stars, and therefore there's an associated probability over the course of a period of time, let's say a year, that a supernova may go off. And so we have worked out a probability of 1 or 2 supernovae per year from the whole set of systems that we are monitoring in real time, or rather that are being monitored in real time by just the nightly sky observations that are going on. So this is really exciting. And we want to test the hypothesis that 1 or more lens supernovae will be able to arrive at its own measurement of cosmic expansion and the Hubble's constant, which is something that is very desirable because it gives us a different set of systematic issues to deal with. When we're talking about Cepheids, there's one range of systematics. When we're talking about lensed quasars, there's a different set of systematics. And so with lens supernovae, we have yet another combination of systematic effects that might be in play. And so by looking at these very different approaches, we have a chance of figuring out what is the underlying truth between all of them and the shared impact, which is the size of the universe and the expansion rate of the universe. So I've not been speaking to these figures in detail, but we have made forecasts as to what the level of precision is that we expect we would be able to measure from our experiment, our 3-year-long experiment. So we are monitoring systems. We plan to follow up with Hubble Space Telescope, and we anticipate being able to measure Hubble's constant with approximately 10% precision with this new independent technique. Now, this is meant to be a pilot for the future, because there are going to be between dozens and up to 100 lens supernovae that will be discovered from frankly, between the Euclid project, the Euclid Dark Energy Project, where I am a member of the science team of the Euclid Consortium. And so I'm excited to see what we are going to be able to do with that. There are surveys from the Roman Space Telescope, the 2.4 meter flagship scale NASA observatory that will launch in 2024 or 2025. And from the Rubin ground-based telescope, which is the LSST project, which will also discover up to 100 or so objects. And here are some specific constraints that my collaborator, Justin Pirrell, worked out and published just a couple months ago on the precision that should be possible from the NASA Roman Space Telescope, which again will launch around 2024 or 2025. The long and the short of it is, it will provide new independent constraints on cosmography, which is to say dark energy, the dark energy parameter W, as well as omega matter, and a Hubble constant measurement that should be measured to a precision of about 1%. And that's based on the order of 30 gravitational lens supernovae in total over the lifetime of its mission. So this is another measurement that we expect will be complete by the year 2030, more or less. So there's quite a lot going on, and there's much work to do for yourselves, for us collaborating together, or for your students. So keep these topics in mind. So Kosta, I'd like to pause for just 1 second, Kosta or Vasily, my kind hosts. And if there's anything that is a burning question, I'm happy to take it. Otherwise, I'll be prepared to transition to the other main through line with gravitational lensing, which is going to be on dark matter.
Yes, there is actually a question from Gina Panopoulou. This is Caltech talking to you through Crete.
I love it.
So Gina says, could you say a bit more about what are the dominant systematic uncertainties for lens supernovae?
Absolutely. Thank you for asking. So the question is, what are some of the dominant effects in lens supernovae? So one of the, so there is a lot of information hanging on how good the sampling actually is. By sampling, I mean the monitoring cadence. If we could create a Hubble Space Telescope quality image of a lens supernova before it reaches its maximum, and then with a cadence of making an image measurement every few hours, that would be ideal in removing some of the fundamental uncertainty in typing the supernova, which is to say in matching exactly what type of supernova it is and what type of light curve it is likely experiencing or producing, because you need to know the light curve in order to measure the delay. And as illustrated in this cartoon in the center, we are functionally getting one image every so often, and each image is capturing each one of the lensed images at different phases in that light curve. And so a fundamental uncertainty is in knowing what the light curve is intrinsically going to be, or characterizing it well enough through the data so that you can actually measure the delta in that time robustly. And the other main systematic that I would call out is that the stellar microlensing that I alluded to earlier, caused by the individual stars in the lensing galaxy itself, can actually cause stochastic magnification variations as the supernova's photosphere is expanding, because you get different levels of microlensing impact, different magnification levels, depending on the angular size of your background object compared to the Einstein radius or the lensing impact size of your foreground stars. And so as the background photosphere is expanding, that microlensing impact is going to change, and it'll change as a function of color. And so having a probabilistic characterization of the microlensing over time at each image position is one of the systematic uncertainties that you have to fold in, and you can absolutely do it. How will you do it ties into how good your lensing and stellar population model is of the foreground galaxy, but it is tractable. There's a really exciting literature just from the past couple of years that is exploring the level of systematic effects. And but there's a huge onus, a huge requirement to high quality observations before and after these time domain observations are taken. So it is a developing field is what I would say, Gina, and I really appreciate the question. I hope this is giving some insight. It is absolutely a work in progress, but I would say that the forecasting that I have alluded to here by Justin Perel does fold in estimates of all of the systematics to the best of our ability today. So, there's some optimism here because it is modeled, but over this time span, there's going to be the opportunity to do a huge amount of follow-up imaging and spectroscopy from the ground with the extremely large telescope and its cousins in the States, as well as from space. So Costa, I think I'll let you curate.
Yeah, thank you, Leonida. There is one more question from Vasilis Hamandaris. Vasilis asks, do you need to have an accurate lens model, often requiring HST imagery in advance, or can you do it after ZTF has initiated the trigger for the HST observations?
No, thank you very much for the question, Vasily. So in the question of how robust of a gravitational lens model does one need in advance, I would say that if you want to forecast your probability of your supernova detection rates, you do need to have a reasonably good gravitational lens model in advance. But if you are working with a very large sample of objects, as we are in our experiment, a reasonably good model is good enough to give you the approximate rates, because a lot of things will average out. But when you want to extract the information robustly, you absolutely need a Hubble Space Telescope class image in order to get the astrometric positions of all of the features very accurately determined, all the surface brightness features of the lens galaxy, the relative positions of the light profile of the lensing galaxy, and anything else that might be in the field. And I am saying Hubble Space Telescope quality because there is an incredible potential from adaptive optics-based ground-based imaging that can be leveraged as well. And sometimes there are surface brightness sensitivity advantages to working from adaptive optics imaging from Keck or VLT or other such platforms as well. But the advantages from space are, I do think, give the edge. But on this kind of timescale that we're talking about here, the Nancy Grace Roman Space Telescope is a Hubble Space Telescope, except with a wide field of view, 2.4 meter size telescope in space with a 0.1 arc second point spread function. So a lot of the required image quality is likely to come from the actual observations themselves. But in the meanwhile, for our observations using the Zwicky Transit Facility and our pilot with our target of opportunity observations, the Hubble Space Telescope imaging that we are going to use for doing the monitoring, we will also use to stack and create the high quality images for doing the more robust gravitational lens models of the individual systems.
Thank you, Leonida. There is one more question by Goris Maravellas. He asks, given that we are looking way back into different galactic environments, for instance, with lower metallicities, is it possible that this approach is an extrapolation of what we infer from supernova in our local universe? In other words, is it possible that we'll see different kinds of supernovae?
Absolutely. And I would say that, excuse me, pardon. Mm. I love the question. So as we look into the past, the metallicities and the star formation histories experienced up to those particular cosmic times are all quite different from the more local volumes that we have studied most supernovae in over the past 20, 30 years. So absolutely, earlier time supernovae could have very different behaviors, very different characteristics, very different intrinsic light curves than ones from our local volumes. And I would say that the evolution or the characterization of each of these systems is part of, it's a valid systematic, I would say cosmic systematic that we need to fold in. And this is where additional observations such as spectroscopy over time will help us do that kind of a diagnosis. But what I'd like to call out in response to that question is that that type of a question isn't unique to the lens supernovae. As we characterize all supernovae at greater distances, we are going to be doing these population characterizations, and we will leverage that information as sort of informational priors to how we then model and interpret the lens supernovae, which will be a small subset of the other supernovae that will be discovered. I will say there's an advantage to the lensed supernovae because there's a magnification in play. So we will be able to get a little extra boost in the photons from the magnification effect, but that will go head to head with the larger numbers that we will be discovering just from the the general field surveys of supernovae. So I appreciate that that is probably an unsatisfactory answer to the question, but it is a very valid observation and one that is folded into these analyses, at least the way that we're anticipating doing the work.
Thank you. Another question by Demosthenis Kazanas. He asks, do we see the de Sitter geometry in gravitational lensing?
There's a little static on the line. Could you repeat the question, please?
Demosthenis Kazanas is actually online, so would you like to ask it yourself?
Well, the question is, do we see, well, we know that, well, we claim that the universe is accelerating, therefore there's a background, it fits well with a de Sitter going from a transition from a Robertson-Walker to de Sitter geometry. And the question is, can we see that? It turns out if you do the standard analysis in asymptotic and flat space, this term, the KR squared term, cancels out, but Professor Rindler suggested that actually it doesn't. It has to do with the angles of measurement, and the angle depends on the background geometry. Have you checked for that? Have we as a scientific community checked for that effect? Is it there?
So rather than going into the different rabbit hole of cosmological frameworks, the way that I'd like to answer right now, Vimo, is that what we're offering here is a variety of observationally independent astrophysical techniques for measuring distances as a function of redshift, which is fundamentally what you use in order to make, fit to any particular model. And so one is able to explore multiple concepts for cosmology and cosmological expansion using these observations. So in making these figures here, yes, this is fitted to a particular specific model. It's for a flat cosmic dark matter dominated cosmological model, but one is welcome to explore other models as well. So another unsatisfactory answer, Vimo. Yes, I appreciate that.
I think, if I remember correctly, they are actually asking about the angle of the of separation of images, but let's leave it here because other people want to ask questions. Yes.
No, I appreciate it. Thank you. So Costa, back to you.
There's one more by Fotis Anagnostopoulos.
Okay.
He asks what assumptions regarding gravity are included and how is the dark matter modeled?
So that is another expansive topic, and that anticipates the next area that I was going to develop, which is on dark matter. Or to tell you what, I'm observing the time. It is the top of the hour, and I would love to at least segue into this other area. So, Costa, I'm going to ask you to please earmark the question, and if I have not addressed it in the next small section, I will develop it a little bit more. Is that all right?
Yes, of course. Go ahead. Yeah.
Okay. And I'm really grateful for the questions as we're going along. It gives a feel of a dialogue, even though we're in this virtual environment. So I really appreciate everybody's questions. So I do need to start with a basic introduction because we are segueing to a different aspect of the gravitational component here. And in fact, let me comment on the question that we just got on the nature of gravity. So this is another area where I am bringing in a particular cosmological bias. The fact is, if I were being very diligent, I would write down Einstein's equation as it applies to the universe, and I would explain that there are two sides to the equation, and that one can work with modifying the nature of gravity, or one can play around with the source of the gravitational component to the universe that is part of and helps drive the evolution of the universe. I have skipped completely over that particular framework and question, which is absolutely valid. There's spectacular work going on the nature of gravity and whether the particular prescription of general relativity applies on cosmologically large scales, and in fact even on galactic scales. And I have not prepared slides that can actually address that in a way that it deserves. So that is my third unsatisfactory answer to excellent questions. But here I'm concentrating on the supposition that we are on the right-hand side of Einstein's equation as it describes the universe, and that there is a gravitational component that has particular features in order to be consistent with what we see from cosmic microwave background and complementary observations of the universe out to the horizon scale. So I'm going to move forward with that conceit, with that supposition, and call out that we have a lot of evidence for something happening on galactic and larger scales that we have long interpreted as a dark matter component. And it's called dark because it cannot be regular matter or baryonic matter, as we often call it in shorthand, because it does not interact in any obvious way with regular matter except through gravity, and it does not produce regular amounts of radiation. So it does not interact with the standard model of particle physics in any clear, obvious way. It also has a cold temperature, cold thermal nature, largely speaking, just because of how we see its impact distributed over a huge dynamic range of physical scales, from galactic scales to the horizon scale. So I've prepared quite a lot of background and introduction, and because I do want to observe the time frame for the colloquium and for our discussion, I'm not going to go into a great level of detail because I want to at least give the connection to the gravitational lensing probe that we've been discussing. I have 2 or 3 slides that motivate how there are multiple ways of searching for the fundamental nature of dark matter. You can go into laboratories deep under mountains. You can go into water or ice in vast volumes and look for indirect measurements there. You can try and produce dark matter in accelerators like the Large Hadron Collider. But we, humble astronomers, are constrained to the cosmos, and so we look for its gravitational signature. So I haven't explained or walked through these diagrams except verbally to explain that there are many different ways that one can explore dark matter. And this is another one that would be, we could spend a great deal of time walking through this. All I'll say about this slide is that this is a theoretician's playground, because there are many, many different well-motivated combinations of properties that a putative, a theoretical particle might have that is allowed or even well-motivated by other interesting puzzles in the universe and by particle physics that could be dark matter. So I'm not going to speak to this, except that it's a really exciting field that I'm very fond of, and I love discussing astroparticle physics. So it's something we can talk about. But in astronomy, in astrophysics, there are many different observations that give us a hint of different properties of dark matter based on how it does not interact in some areas with baryons, but does give a gravitational signature. And so I have a large laundry list of observables, some of which you might be very familiar with, whether it has to do with satellite or dwarf galaxies, or the Lyman alpha forests from the intergalactic medium, or the kinematics and dynamics of stellar streams in the Milky Way galaxy or in the Magellanic Clouds, to shapes of galaxies, to the phase space density of satellite galaxies or even of giant galaxies, and so on. It's exciting. And the fundamental puzzle is the who cares? How do you make the connection to actual physical properties of dark matter that then allow you to go and have an intelligent and intelligible conversation with our particle physics colleagues? So we go back to the gravitational signature, and that has to do with the distribution of matter on different physical scales, and particularly on small scales. And if you're familiar with the encoding or the shorthand of the power mass spectrum, that has to do with these small scales or galactic and subgalactic scales. So I won't speak to this diagram here, but I'll speak to its sister diagram here, which motivates that here in these, on the right-hand side of these diagrams, I am showing how much information or how much fluctuation there might be on galactic to subgalactic scales. So where you see these different plots diverge is on these smaller type scales. And when I say standard cold dark matter, or CDM, that's the vanilla model of the entire universe. And when you see these other diverging figures, that is for other models for dark matter that are motivated by our particle and astroparticle physics colleagues. So there could be very massive particles, there could be warm dark matter, there could be self-interacting dark matter, all these very novel terms that, that may describe the real universe. The point is that when we are looking at galactic kinds of scales, the amount of smaller scale structure within a galaxy can look very different depending on the nature of dark matter. And so cold dark matter on the left in this simulation is very, very rich. And these features can go all the way down to, literally down to something like 10 to the minus 6 times the mass of the sun, self-gravitating halos. That's the size of a Jupiter, or 10 to the minus 9 solar masses, which is the mass of an Earth. Although, of course, much more broadly or rarely distributed in density than an actual planet. But then warm dark matter wipes out those scales, and you're left with the smallest scales being maybe 1 million times the mass of the sun. So very, very different ansatses for the universe, as it were. So very different predictions. And now I will try and come to a rapid conclusion. The point is that in gravitational lensing, it is possible to see the gravitational imprint of dark matter substructure if you are clever, extremely patient, and you have the right kinds of observations. And this diagram just motivates that you might get a different kind of an impact from these different scales of predicted kinds of structure. And you might remember the arrival time equation that we dwelled on for a moment. Earlier, we talked about the leading term for cosmography, and now we get to dwell with the phi of that vector position he, which is the projected gravitational potential. And that is where all the exciting things happen. Because time delays, the differences in arrival time, scale directly with what's going on with the gravitational potential. The image positions you get by the first derivative of that arrival time surface that I plotted earlier that you see here. And the magnifications, it's actually the inverse magnifications, have to do with the second derivatives of, so basically the inflection points of where those images form. So small fluctuations in the gravitational potential can give you huge differences in the relative magnifications. Small fluctuations in the gravitational potential can modify the actual positions of these lensed images. And small fluctuations in the potential can actually modify the arrival time of light between these images. So there's rich information that you can already, I can just picture you right now raising your hands already, that we've talked about all these systematics that are in play with the other techniques for cosmography. Well, you'll be satisfied to know they are all in play here as well. The problem is very complex, but depending on your observations, it is also very tractable. So I'm going to skip over some of the exciting hints that we have that gravitational imprint in gravitational lenses is detectable and real, and I will tell you one conclusion from the literature to date, and then I will motivate one exciting experiment I am part of, and then I'll conclude to not impinge on your time and your patience much more. So in lensed quasars, work that my colleague and friend Daniel Gilman published just a few months ago, one is able to bring in the full complexity of what you might expect in a gravitational lens system. By full complexity, I mean the impact of microlensing statistically, the impact of gravitational lensing material from the entire line of sight between you and the lens and the background object, and the uncertainties to knowing what is actually going on in the lensing galaxy. And if you fold in sufficiently sophisticated lens models that allow you to bring in the information that we have about the universe in a robust Bayesian framework, you can start to marginalize over all of these other systematics, which I would frankly call signal, if you're interested in different things. And you can start to constrain how much dark matter substructure there is down to subgalactic scales. And so this figure, this box on the right that I've highlighted, the bright red star, is what I would call one of the most state-of-the-art measurements to date using gravitational lensing. Now, this may or may not mean a lot to you, but I am very excited about this. The limit of the dark matter mass, particle mass of being greater than 5 keV points towards, well, rules out some huge swaths of warm dark matter candidates. And it points to the direction of what is still allowed in this interface between astrophysics and particle physics. So this is a big deal. And this is sort of giving a hint as to what we might be able to accomplish with more and improved measurements. The experiment that I want to mention is one that builds on a paper that I published with Ben Metcalf going on 20 years ago when I was a postdoc at Oxford, on leveraging the multiple scales in quasars and observing that when you have some features from the spectrum of a quasar come from the full galaxy scale structure of the host galaxy. That's the narrow line regions. Whereas the continuum is coming from the compact accretion disk area, and that's hugely impacted by stellar microlensing, as we discussed. But the broadline region is this intermediate scale feature in a quasar, that's sort of in a sweet spot. It's not really impacted that much by microlensing, but it's just the right kind of angular scale to be impacted by the dark matter substructure because of the angular size that it has. And so if you get spectroscopy of multiple images in a quasar, you can reverse engineer that and make inference on the dark matter substructure in a sort of a sweet spot of mass scales. So this is an experiment or measurements that my colleague, Professor Anna Nierenberg, has been conducting for several years now using Hubble and Keck observatories. And I cannot tell you how exciting this is because it has been producing some very exciting direct measurements of the influence of substructure spectroscopically. And we've just been awarded a Cycle 1 observation program with the James Webb Space Telescope, which launches in October of this calendar year. And it is to observe, let me shift, there we go, to observe 16 lensed quasars in a way that we will be able to do this sort of matched size scale mapping using the sweet spot multi-wavelength imaging for these objects. And we will have sensitivity down to 10 keV of the dark matter particle. So a vast improvement over what is possible today. And this is a measurement that we anticipate we'll be able to deliver within 2 or 3 years of when observations actually start. So I am going to skip over another main area that I am very, very fond of and that I'm working in. I will put up the conclusion highlights from this very rapid tour of using strong gravitational lensing as a tool for cosmography, dark energy, Hubble's constant, dark matter, and more. And I will open the floor to a few more minutes of questions if there are any. I just want to profoundly thank you for your attention and your patience and for joining me on this virtual colloquium day. So Costa, I'm going to give it back to you.
Thank you, Leonida. I don't know, can you hear me now?
Yes, I can hear you perfectly.
Okay, so thank you very much. Are there any questions remaining? We still have time for maybe a few, 1 or 2 questions. If somebody wants to open their mic.
By all means.
There you go.
Okay.
So, Nico.
Okay. Give it to Nikos. Okay. I already asked.
So, all right. A naive question, Leonida. In nearly all the images that you showed, there are of lensing, there are 4 images. Is that an accident, or and I knew that the number of images is odd, so I assumed that the 5th image is where the galaxy is.
Yes. No, thank you for asking the question, Nico. I really appreciate it, and I love. I love the potential elegance of the answer, and hopefully I will live up to it. So this all goes back to this simple equation, which is the arrival time equation. And this figure, this contour plot that I've added here, is it's a contour of this quantity tau, this arrival time equation, and so these contours are encapsulating all of the information that is on the right-hand side of the equation. So the relative alignment and the gravitational potential structure. Now, what happens when you have a gravitational potential that basically is fairly regular, fairly smooth, going from a particular peak to smoother outer regions, you will always get an odd number of inflection points, and it comes out as simply the topology of this equation. So yes, there are always an odd number of images when everything is smooth, like you see here. So in fact, there is a central image that is demagnified, and so we tend not to speak of it because the outer images tend to be magnified, and so they are more prominent. So you can end up with 3 image configurations where the 2 of the 3 images are the ones that tend to be brightened, 5 image configurations where the 4 are brightened, and you can go to much higher numbers as well, depending on the actual structure of the projected potential. There are situations where if you break that sort of smooth potential assumption, that you can get different numbers of images, and those are called catastrophes, which can tell you a great deal about the small scale, the particular structure that deviates, that allows you to deviate from that smooth assumption. But that's sort of this topological description of a time delay surface is the origin of that odd number theorem that you alluded to, Nico. And I really appreciate the question. Thank you.
Thank you, Leonida.
Thank you.
I understand that you have to go soon, but
Yes.
if it's a
May
quick
I ask
question-
a quick question?
Okay,
May I ask a quick question?
please go ahead.
Very nice talk, Leonidas. Just a quick question. Is there any intrinsic assumption or calibration on the underlying cosmology and or the underlying theory of gravity and whether dark matter should be multi-component or not? I mean, is your formalism ready to detect deviations from GR or from lambda CDM cosmology?
No, thank you for the question. As I mentioned earlier, all of this is intended to be insightful measurements into the universe that one can apply to different assumptions for the cosmological or dark matter model that might describe the universe. So in a sense, I'm coming in fairly agnostic. And I know that there is literature where how this can be applied to constraining alternative gravitational models or gravity models or dark matter models has been used. I am less familiar with the literature. And I think my understanding is that there are some, that the measurements are not constraining enough to give deep insights into the alternative models. Whereas in this prescription, we are able to actually get some insights into this particular framing. This is, I think, my 4th unsatisfactory answer to an excellent question. But maybe I can answer a variation of what you asked in terms of multiple components of dark matter. So I'm going to say that I'm agnostic there as well, but in a sense, this is a positive. So in this summary of cornucopia of dark matter particle models, there are so many different possibilities to what dark matter might be, and quite a few of them actually we will never detect with the Large Hadron Collider or with any direct detection experiment we can conceive of, just because they are so elusive in how they do not interact with regular matter or radiation fields. But it is entirely possible that one or many of these could make up dark matter. I think the way I think of it is, since the standard model has such a rich diversity of particles and fields, why should dark matter be any different? Why does it need to be a single particle? I think it's plausible that there could be an entire family or ecosystem of particles that are following their own fundamental new standard model that we have yet to fully decipher, that could be making up dark matter. The other hint here is that to the limit of our ability to measure the cosmic microwave background and what the behavior of the universe is on very large scales, we are seeing that the universe is flat. Omega total is equal to 1 to a couple %, maybe even a little better than that. And that is telling us that the sum of regular matter, dark energy, and dark matter are giving us that flatness. So I would say that it's plausible that there's some underlying feature to the universe that is allowing for the combination of whatever is making up dark matter, one or many different species, that is driven to that that sum that ends up giving us that flatness in the universe. So there's many different layers to this that are intriguing, I think. And the nature of gravity, as well as the nature of gravity in terms of cosmic expansion, and then the nature of gravity in terms of this gravitational signature, I think it's an open field, and how they play separately or together is it's something that I'm hoping we'll get deeper insights in as we do more experiments like this. So I really appreciate the question.
Thank you. Thank you.
Thank you, Leonida. I understand that.
I have one question. Sorry, can I ask?
Okay. I
Sure.
don't know, Leonida. Do you still have a few minutes?
Yes, I do need to move on to my next commitment in about 2 or 3 minutes, but I'd be delighted to answer.
Okay, sorry for disrupting, but I want to ask, how do you selected your quasars? Because I was wondering, how did you deal with mass sheet degeneracy? So if you have to deal with that, then you have to point out like some special quasars which are less affected by them. So how I saw you have 4 quasar images. So I don't know, how do you deal with it, or how did you selected this quasar for lensing?
No, thank you for the question. What's being alluded to here is the mass sheet degeneracy, excuse me, which is that everything else being equal, when you see a 4-image lens like one of these systems here, you can write down a model pretty trivially. You just need, maybe 4 or 5 lines of Python code, and you can produce a gravitational lens model. I encourage you to go and try it. But you'll find that there is a basic degeneracy in the simplest models between the profile of your gravitational lensing potential and a flat contribution from the environment, basically a sheet of mass, and that's the origin of the mass sheet degeneracy. So the fact is that one is able to, well, you can do 2 things. One is you can actually break that degeneracy if you also have kinematic or dynamical information of the lensing galaxy, because then that allows you to constrain what is actually going on in the gravitational potential, and that gives you that extra factor to disentangle the environment from what is going on in the primary gravitational lensing potential. And that's a development that is that's evolved over the past 20 years, but the mass sheet degeneracy has been very pernicious for a very long time. The other ingredient that has basically come from, I'll say, years of hard work and improved sophistication in our modeling is that you can actually fold in the uncertainty, the remaining uncertainty to the mass sheet degeneracy when one is doing these kinds of analyses. And that's what we do. So in fact, we've taken this to the next layer of complexity. We're not just folding in what the mass sheet type of degeneracy might be in the plane of the lensing galaxy, but we actively and quantitatively fold in the uncertainty from whatever might be happening from the entire line of sight of material, from just the potential fluctuations you might get and the impact they might have in this projected surface mass density plane that's doing the lensing from all of the material. And so the sophistication to this has improved a lot. And the Python lens modeling package that I alluded to earlier, called Lenstronomy, does a very nice job of folding in a prescription for line of sight material, as well as uncertainty in the mass sheet, as well as what might be going on in the lensing galaxy. So the shorter answer to your question would be that our sophistication has increased a great deal, and we're in a much different place now than even 4 years ago, 5 years ago, in being able to evaluate the value of individual systems and then leveraging them for specific measurements. I can't tell you how excited I've been from the past 5 or 10 years of development in this area, because your question is the spot on one for how we need to continue to mature. So thank you for the question.
Thank you for the answer. Thank you so much.
My pleasure.
Thank you, Leonida. I understand you need to go.
I do.
So again, thank you very much for this beautiful presentation and the very interactive style. And thank you all for coming tonight. Have a good evening.